Hello and welcome to this first episode of Quest for Fire. My name is Andre Muscat, fire engineering graduate from the University of Central Lancashire. In this first video, we will be analyzing the basics of fire development. We will be using an old but very good fire safety training video and the modern tool of Computational Fluid Dynamics. The video we will be analyzing was produced by the National Fire Protection Association, NFPA, and the CFD program is FDS, developed by NIST, the National Institute of Standards and Technology. The NFPA video recreated a normal sitting room with all its furnishings and was ignited with the use of a small electric coil. This acted as a piece of smoldering material. After ignition, the fire was left to develop naturally and observed. The room was recreated three-dimensionally in FDS as close to the real experiment as possible. But due to the absence of actual dimensions and documentation on the material, all the measurements had to be estimated. The fire was set to start on the horizontal surface of the sofa, in the diagram shown in red. It was programmed to spread in a slow t-squared manner, as would be expected in a fire of this sort. At first, the fire started off in a smoldering state, but after a while the fire progressed into a flame-producing stage. It is still a very small fire, but it will continue to grow as it warms up the material around it. At this point, the heat from the fire would be producing combustible gases or pyrolysis products. The buoyancy of the heated gases causes them to travel upwards, which contributes to the heating of the rest of the room. In this situation, a curtain is located above the initial fire. This will start to take heat from the flames and the rising smoke plume. We can continue to watch the video until the curtain ignites. It is worth noting that the three-dimensional reconstruction is made to run at twice normal speed, and here the reconstruction is run until ignition of the curtain occurs. If we go back to the video to a few moments after the curtain ignited, we can see that the fire is now growing significantly strong, and that signs of intense heat spread can be seen throughout the room. Also very noticeable is the thick black smoke that is now billowing out of the room. A few moments after this happens, the phenomenon known as flashover occurs. Here the remaining surfaces not yet on fire ignite almost simultaneously. The details of how and why this happens will be studied further with the use of the computational model. Here we can continue to follow the growth of the fire from the ignition of the curtain onwards. With the help of CFD, we can switch off the smoke layer so that the flame spread is visible without obstruction. The surfaces in green are the surfaces that have been programmed through FDS to auto-ignite at a set temperature of 125 degrees Celsius. Once the flame starts to spread, the heat transfer to the other fuels increases rapidly. In a short time, we achieve temperatures that involve the rest of the materials in this compartment. Remember that the simulation is speeded up at higher than normal speed. We will now use the simulation to analyze more closely other key aspects of the development of this fire. This will show us how the temperature distribution was at various points during the simulation. It is easy to notice that the highest areas in the room are the hottest, while initially the lowest parts have very little change. In the simulation, flashover occurs between the 240th and 270th second. At this point we can see that the top layer has reached temperatures in excess of 650 degrees Celsius. More significantly, the lower layer has experienced a sudden spike in temperature. Something else we can do with CFD is observe the movement of gases. During the initial moments of the simulation, we can notice the upper layer moving outwards with the smoke, while little movement is noticeable elsewhere. Further into the simulation, while faster movement is seen at the top layer, we can observe a flow of air moving through the bottom layer. During the final stages, while both previously mentioned movements have increased in intensity, a turbulent mixing of gases can be seen in the middle section. Without the use of a powerful tool such as FDS, we would need to resort to hand calculations to obtain information that we need about the fire. Each time we carry out these calculations, we would obtain either the temperature or the velocity of the smoke at one particular position in the room. CFD does the same, but it does it for hundreds and thousands of times. It also does it for all the areas in the room. This gives us a more accurate and dynamic picture of what is going on within the environment being considered.